Hi, Assalamualaikum and a very good morning. So now we're going to do chapter 7, which is Haloalkane. We're going to focus on the subtopic of 7.2 chemical properties, focusing on part 1 of the video first. So in this video, we're going to look into the description of haloalkane, where haloalkane will have a general formula of Rx, where X here refer to a halogen. So we're going to look into the polar bond and where the polar bond going to be susceptible for the nucleophilic attack. So susceptible here means that it's going to be an easy target or lebih mudah untuk dia undergo nucleophilic attack. So on the next part, we're going to explain the nucleophilic substitution reaction where we're going to look into two types, which is SN1 and SN2 mechanism. On last part, we're going to compare the relative reactivities of the primary, secondary, and tertiary haloalkane towards hydrolysis and alcoholysis. So hydrolysis happens when the nucleophile gonna be a water or it's gonna have a hydroxide ion. So water here is a neutral molecule, and hydroxide ion here are gonna be the negative charge or an ion. For alcoholysis, it's gonna be happening when the nucleophile will have OR minus here. So R here can be OCH3 or can be OCH2, CH3 or any alkyl chain. Okay, so this come from the alcohol group, which is CH3OH. Okay, it's gonna be CH3O minus when it is becoming an ion, and this one comes from base, and this comes from the water. All right. So without any further ado, let us start. So haloalkane, which containing a carbon halogen bond, is a very polar bond because the halogen here is going to be more electronegative than the carbon. So the electron density going to move towards the halogen group. So due to the electronegativity of the carbon atom, this carbon here will carry a partially positive charge, and this halogen group here going to carry a partially negative charge. And because it carries a partially positive charge, it will be an easy target for the nucleophile to attack the carbon. Okay? And this refers to the electrophilic side. And in a reaction, they're going to be a nucleophile and they're going to be an electrophile. So due to these properties, the haloalkane can undergo nucleophilic substitution reaction. And in the latter video, you're going to see that the haloalkane can undergo elimination and it can be used to synthesize the green reagent. However, in this video, we're going to focus on the nucleophilic substitution reaction first, which is in the part 1 of the video. For these two reaction later, you're going to look at it at part 2. Okay? So for the nucleophilic substitution reaction, there are two types and the mechanism going to be depending on the structure of the haloalkane. So haloalkane, as you have looked in the previous video, haloalkane can be divided into primary, secondary or tertiary. So this classification is important in order to determine the type of mechanism or the type of nucleophilic substitution reaction that are taking place. So there are two types, which is we have the unimolecular nucleophilic substitution, and second we have the bimolecular nucleophilic substitution. So substitution here refers to the letter S, nucleophilic refers to the letter N, and uni refer to 1. Okay, same goes to here where S refer to the substitution, nucleophilic refer to the N, and bi refer kepada 2, right? So it's gonna be SN2 here. Okay, and in order to determine whether the reaction or the haloalkane undergo SN1 or SN2, we're going to look into the class of the haloalkane. So for the primary and methyl haloalkane, it will usually undergo SN2, where it is the usual case where it has a low steric hindrance. So low steric hindrance means that it is not protected by big group. Okay, maksudnya dia attach kepada atom-atom yang kecil. Kalau dia attach pada atom yang besar, it gonna have a high steric hindrance. For example, if you have CH3 CCH2Br. Okay, so we're going to look into this mechanism in the later slide. However, when the haloalkane has a secondary classification, it will be depending on the strength of the nucleophile. So, if the nucleophile used in the reaction is a strong nucleophile, for example, hydroxide ion, methoxide ion, carboxylate ion, or cyanide ion, it will undergo SN2. However, when the nucleophile used is a weak nucleophile, it will undergo SN1. So the example of the weak nucleophile is water, alcohol, for example, the ethanol here, and also the amino group, which is an amine or ammonia. Okay, so as what you can see here, the strong nucleophile usually will have a negative charge. Meanwhile, for the weak nucleophile, usually it existing as a neutral molecule. For example, water, where it has a lone pair, but the overall charge here is neutral. Same goes to ammonia, when it has a 3 NH bond and 1 lone pair. So this is known as a weak nucleophile. So for the secondary haloalkane, when a strong nucleophile is used, it will undergo SN2. If a weak nucleophile is used, it will undergo SN1. Meanwhile, for tertiary haloalkane, it will usually undergo SN1, and we must use the weak nucleophile in order for the SN1 reaction to occur for the tertiary haloalkane. Okay, so this flow chart here is very important and going to be used along the process here. So it is important for you to at least memorize it at first and try to understand it as you go along. Okay, so now this is the differences between the SN1 and SN2 mechanism. So for SN1, because we're referring to one, so it is focusing on the unimolecular nucleophilic substitution reaction. And because it one, we are saying that it is a first order reaction and the rate going to be dependent on the concentration of the haloalkane. Okay, the other name of haloalkane going to be the alkyl halide. Okay, dia bergantung kepada kepekatan oleh kepekatan haloalkane tersebut. And usually for SN1, the weak nucleophile is being used, which is the neutral molecule I have talked just now. For example, water and ammonia. So for SN1, it involves the carboxyl ion as intermediate, and the rearrangement can occur. So for SN1, it's gonna be having two-step mechanism. And for SN1, the tertiary haloalkane gonna be the one that will undergo more reactive towards SN1 mechanism. And here you can see that the steric factor is not quite important. Okay. So for SN2, it is a bimolecular nucleophilic substitution, and because it refers to number 2, it is a second order reaction where it's going to be depending on the concentration of the haloalkane and the concentration of the nucleophile. So dia bergantung kepada kedua-dua, concentration untuk haloalkane tadi dan juga nucleophile yang digunakan. So in SN2, we're going to be depending on the nucleophile, the strong nucleophile, which is hydroxide, methoxide, and cyanide, and so on. And here, in this step, it involves the activated complex, and it refers to the one-step mechanism. And for this SN2, the methyl halide gonna be more familiar to the SN2 mechanism. So primary and methyl halide gonna be the best one for SN2. And here, the steric factor is important. So this is the differences between SN1 and SN2, and so that whenever you got confused, you can always refer back to the properties of SN1 and SN2 here. Okay, so for SN1, it's going to be a first order reaction. So SN1, it will have two-step mechanism, and it involves a tertiary carboxyl ion beta. So ingat 1, 2 dan 3. For bimolecular, we are referring to SN2. So it's going to be 2 involve one step, and primary haloalkane will be better for SN2. So 1, 2, 3 and SN2 going to be 2, 1, 1. Okay, so these are the key point idea. So now we're going to look into the SN1 mechanism first. Macam cerita, SN1 going to have 2 step, dan dia melibatkan tertiary carbocation. So ingat 1, 2 dan 3. So you know that it consists of 2 steps. Okay, so first we're going to have, for the SN1 reaction to occur, first we need to identify whether it is a tertiary carbocation or not. So this carbon is attached to the halogen. The carbon here going to have 1, 2 and 3 alkyl group attached to it. So it is a tertiary carbocation. So for the step number 1, the bond going to be broken between the CX bond, and this going to produce a positive charge on the carbon, and because electron is being transferred to halogen, it's going to carry a negative charge. And because it carries a partially positive charge, okay, so the partially positive charge going to be attacked by the nucleophile into here. And as a result, the nucleophile going to be attached to the carbon bond. And the nucleophile here can be, for example, water or hydroxide ion. Okay, and this can be represented as in the diagram here. So for SN1 reaction, it involves 2 steps. First, you need to remove your halogen first. Kamu keluarkan kucing, kelabu dahulu, and then baru nucleophile, which is the orange cat, to enter the empty spot. Okay. Meanwhile, for SN2, as what you can see here, SN2, it involves only 1 step. Okay, so the strong nucleophile going to be used here, and it will directly attack the electrophilic site. And then this causes, when the nucleophile enters or attack the carbon, the nucleophile gonna almost forming the bond with the carbon. At the same time, the CX bond here almost broken down. So this is why we are denoting it with a dash line here, garisan putus-putus. And this process here is known as the activated complex. And at the end, you will directly form your nucleophile here. Yang mana nucleophile masuk dan X akan keluar. Okay, X akan keluar membentuk X minus di sini. Okay, so sebenarnya dia adalah satu step. Tetapi for a mechanism, you need to show that it form a activated complex first, then only forming a product here. Alright, so this is the representation where a strong nucleophile gonna chase away the halogen group, where it will form an activated complex. Then the nucleophile akan masuk and the halogen gonna go out. Alright, so remember that for the nucleophilic attack, it's gonna be a backside attack. Maksudnya dia attack daripada belakang daripada halogen, and the intermediate, which is activated complex here, need to be shown. Alright, and at the end of the mechanism, you can see that the line here gonna be having an inverted configuration. So it was started out as like this, macam satu penyapu. Sekarang penyapu kamu adalah dalam bentuk macam ni. Okay, so first they are like this. At the end of the reaction, it's gonna be like that. Initial, and this is the final. Okay, now we're going to look into the specific example here. So let's say if we have Rx, which is our haloalkane, reacting with water, which is our weak nucleophile, under reflux. So you know that our OH going to enter here, and the halogen group going to be removed. So water here act as a weak nucleophile. So let's say if you are given a situation here, and this process is known as hydrolysis using water, which is a weak nucleophile. So as what you can see here, the carbon here going to be a tertiary haloalkane because it is attached with 3 alkyl group. Okay, so it will undergo SN1 reaction. So you can always refer back to the flow chart here. Tertiary akan undergo SN1. So now let us draw the mechanism. Okay, so you know that SN1 will involve two steps. Okay, tu cara ingat dia. And it gonna occurs for tertiary carbocation ion. So this is the tertiary carbocation ion. So step number 1 is we're gonna break the Br bond here first. And then this is known as a slow process, or in other words, it's gonna be the red determining step. Okay, and the break of the bond between carbon and halogen group gonna transfer 2 electron to the bromine, and this carries a partially positive charge on the carbon, and the bromine gonna carry a partially negative charge. Okay, because usually the bromine here gonna have a lone pair, but now because 2 electrons are being transferred here, it's gonna have 8 electrons in total. However, when we calculate the formal charge, it's gonna be 7 because bromine will initially have 7 valence electron minus 8 electron that they have as the lone pair electrons. So it's gonna carry a negative charge here. However, for the carbon will have 4 valence electron and it is attached with 3 carbon minus 3. So it's gonna carry a partially positive charge, which is +1 for the carbon and -1 for the bromine. Okay, now for step 1 is done. Now we're going to do the step number 2, which is the nucleophilic attack. So because we have a partially positive charge here, our nucleophile here is now a water. So water is the weak nucleophile. So water will use its lone pair and use to attack the C plus here. And this is a fast reaction. And the O will attach to the carbon. And the oxygen here will carry a partially positive charge because oxygen will have 6 valence electron minus 1, 2, 3 single bond and 1, 2 lone pair electron. So you're going to carry a positive 1 charge. Okay, but now we're going to produce CH3, 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 OH. So we have to remove 1 hydrogen here. So another water molecule in the beaker, for example, will then be used to attack one of the hydrogen, and this is going to break the bond in between the OH and transfer 2 electron to the oxygen. And as a result, you will get the oxygen here will receive 2 electron, and hence the oxygen will now have a neutral charge because oxygen will have 6 valence electron minus 2 bonding pairs and 1, 2, 3, 4 lone pair electrons. So it's going to be 0. This one here is oxygen. Okay, so we're going to and we basically have shown our major product here, and as a result, OH here going to have a H3O plus ion. Okay, and you can continue to use your Br to attack the hydrogen, and here going to attach to here again in order to get HBr. However, this step is usually not required because we only need to show until the major product here. Alright, now moving on to the next example here. So now we're going to do the hydrolysis with the hydroxide ion. So let's say if you have sodium hydroxide. So the hydroxide ion comes from the dissociation of the NaOH. So OH minus here going to be a strong nucleophile because it carries a negative charge. So OH going to enter here and X going to be removed out. Okay, and this produce an alcohol. So the first thing first, we have to know our nucleophile, which is a strong base. And if we look into our reaction here, it is a primary haloalkane because it is attached with one alkyl group. Okay, so it is a primary haloalkane, and then it is attached with only one alkyl group. So one alkyl group will have low steric hindrance and then it will undergo SN2. Kalau high steric hindrance, semua ni akan attach kepada 3 methyl group ataupun bulky group, atom yang besar. Tapi for this one is a small atom. So in this case, it will undergo SN2 reaction as shown in the flowchart here. Okay, now let us look into the mechanism. So first we draw again the structure of the given haloalkane, which is our primary haloalkane, and we need to draw it in terms of the 3D structure. So two of the atom is in plane, one out of plane and one behind the plane. Okay, and the hydroxide ion come from the NaOH will then be used to attack the electrophilic site. Okay, and this causes the breakdown of the CBr bond where the 2 electrons will be transferred into bromine. And this is a slow start reaction. And as mentioned, we need to show our transition state. So the transition state involves the partially bonding between the attacking nucleophile and the haloalkane. So maksudnya ada garisan putus-putus antara nucleophile yang baru masuk dan yang akan keluar tadi. So this gonna be our transition state. So bonding seakan-akan hampir nak terbentuk. Dash, dash, dash. Dan CBr ni hampir-hampir nak terputus. Dash, dash, dash. Okay. And at the end of the reaction, okay, we can say that it is a fast process where OH betul-betul form dia dah terbentuk dan Br ni betul-betul dah terputus. So you're gonna plus Br minus here. Okay. And as what you can see, here going to carry a partially negative charge because it is a nucleophile. And here is the electrophilic site, so you're going to carry a positive charge. And here is the nucleophile, which is a negative charge again. So it's going to be negative, partially positive, partially negative. Okay. And as mentioned, for SN2 mechanism, dia seolah-olah macam penyapu. Okay, at first you're going to draw it this way, but at the end of the reaction, it's going to be the inverted way. And you have to show the transition state. So, in the SN2 reaction, the nucleophile attack from the backside, dari belakang, of the electrophilic carbon that is from the side directly opposite bonded to the halogen. And at the same time, the backside attack causes the product form to have inverse configuration. So, here is the inverse configuration from the original configuration. So from this Y shape penyapu menjadi penyapu yang terbalik. Alright. So now we're going to look into the reactivity of various haloalkane towards the nucleophilic substitution reaction. So antara iodoalkane and bromoalkane, chloroalkane and fluoroalkane, which one is more reactive towards each other, towards the nucleophilic substitution reaction? So we can say that iodoalkane going to be more reactive than bromoalkane, and it is more reactive than chloroalkane, and it is more reactive than fluoroalkane. This is because the strength of the carbon halogen bond increases from iodine into fluorine. So iodoalkane here will have the least strong bond ataupun weakest bond. Ini adalah strongest bond. So weakest bond here going to be the most reactive species. This is because when the Ri here, which is the weakest bond, it is easier to break the bond, and hence easier for the molecule to form a carbocation and leave out the halogen group apart. However, in this case, if R and F bond are strong, it is very, very difficult to break the bond. Hence, it is less reactive. Okay, and R here refers to the alkyl group. So, it can be CH3 or it can be CH2, CH3, and so on. Okay, so you can imagine it as CH3I or CH3Br if they were to coming out in the equation and they ask you to compare. So remember, weakest bond is the most reactive bond. Okay, because it is easier to break the C and I bond apart. Okay, now we're going to look into the steric effect. Okay, for the steric effect, it basically means that it is the effect on the relative rate caused by the space filling properties of those part of the molecule attached at or near to the reacting site. So here we're going to have a primary haloalkane. Okay, carbon ini hanya attached to one alkyl group. So usually we're going to say that it will undergo SN1 reaction. And the steric effect here means that it is the space filling properties where the carbon gonna attach with a small atom or not. And as you know, hydrogen is a small atom. So there will be no steric effect. Okay. So if primary haloalkane, it will be easier for the primary haloalkane, it will be easier to undergo SN2 mechanism. However, as you were to look into this case, okay, we have CRRR CH2Br. So if I were to expand the structure, I'm gonna get CH, CH, and CBr here. So we can say that the carbon here gonna be our primary haloalkane because the carbon here gonna attach with one alkyl group. Carbon ni attach kepada satu alkyl group. However, this primary haloalkane with large alkyl group, okay, dia ada alkyl group yang sangat-sangat besar, and this menyebabkan this primary haloalkane will not undergo SN2. Dia tidak sama macam yang ke atas, and this is because due to the steric hindrance. So primary haloalkane bila dia ada high steric hindrance, for example CH3CCH2Br, it will undergo SN1 mechanism instead. Okay, so because of the more steric effect, it will not undergo SN2 but will undergo SN1. Okay, so let us look into the mechanism here and the example. So let's say if we have a structure of CH3, 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 and this carbon here, as mentioned, is a primary haloalkane. Okay, if you were to expand it this way. So it is primary haloalkane. So if you follow the chart, usually the primary haloalkane will undergo SN2. However, because of the large alkyl group here, it will undergo SN1. Okay, and as mentioned, SN1 will have two steps, and usually it will undergo for the tertiary haloalkane. However, because of the primary haloalkane that have a steric hindrance, it can undergo SN1. So the CBr bond first gonna be break apart, and this causes the carbon here gonna have a partially positive charge due to the formal charge. So you can count the formal charge by your own, and the Br gonna carry a Br here gonna carry a negative charge here, and this causes the carbon here to be a primary carbocation. So this is not good, and hence what we're going to do is we're going to do the rearrangement. So we're going to bring the CH3 group here to the right hand side. Okay, and this process is known as 1,2 methyl shift, and as we bring the methyl group to the right hand side, it will carry a positive charge here. Okay, and the positive charge here will have 1, 2, 3 alkyl group. So it's going to be a tertiary carbocation. And now we can enter our nucleophile. So our nucleophile here is KCN. So if they were to dissociate and form ion, it's going to be K plus and Cn minus. Okay, Cn minus. So the the carbon gonna carry a negative charge. So the Cn gonna be used to attack the C plus, which is the electrophile here. Okay, and remember the carbon gonna carry the negative charge, and as the result the carbon gonna be attached with the carbon plus here gonna be attached with the carbon minus here, and this gonna form the CCN bond here, and this shows the product that we are forming. So we have CH3, CH3, Cn, and CH2CH3, which is CH2 and CH3. Okay, so I think that's all for today's video. See you again in some other time. Bye.